Many times we're not able to come up with a formula for the sequence of partial sums, and therefore trying to determine whether or not that has a limit and whether or not that series converges is very difficult. So a lot of the rest of our unit is about learning different tests that we can do to determine if a series converges or diverges without having to have that formula. The first one is a very, very powerful one. It's the nth term test for divergence. And it says that if the limit of the sequence that is generating the series, if that limit is not zero, then the series diverges. Very important that you don't turn this around or misuse it. If the limit of the sequence is zero, you don't know anything. The series could converge, the series could diverge, and in fact we're going to see examples of both of those cases. So it only works in one direction, which is the limit of the sequence is not zero, then the series diverges. But even this can be very helpful to get a start on looking at some series. So if we want to determine if the following series converge or diverge, the first thing I would do is to think about the term expression, which is 5n squared plus 7 divided by 4n minus 9n squared. I feel like I'm going to run out of room if I don't move that up here maybe. Alright, so if I do that, then the limit of those terms as n goes to infinity of the a sub n. This is a piece where I'm a little bit pedantic and like to put in a good bit of extra notation. It's going to be helpful later that we actually do name the formula for the sequence. So in this case, we could have just jumped right into finding the limit with this expression without having to rename it. But it'll come in handy on other problems. So I find this limit. When we were talking about sequences, we know that we can compare it to a real variable function, 5x squared plus 7 divided by 4x minus 9x squared. That's a rational function. We know that its limit is the ratio of the leading coefficients since the degrees are equal. And if the limit of that real variable function exists, then it's the same as the limit of the sequence. So this sequence has a limit of -5/9. That is very definitely not zero, and therefore the series given by that expression from n equals 3 to infinity, or in other words the series that I was asked about from n equals 3 to infinity of 5n squared plus 7 divided by 4n minus 9n squared diverges. I'm going to write that out with letters. Diverges by the nth term test. We always want to say what our reasoning is there. If we're using a theorem, we want to invoke it. I will point out that this part here, and this part here could have been left off and the meaning still would have been there very clearly. But there are some cases later where putting those in is going to be useful. Alright, so in this example here, I'm going to let a sub n equal the square root of n divided by the natural log of n. And I really want to look at that limit as n goes to infinity of those terms. That means finding the limit as n goes to infinity, the square root of n divided by the natural log of n. Well, if I think about the real variable function here on this one, the square root of x divided by the natural log of x, we know that that actually diverges. We did enough work with L'Hopital's to know that an algebraic function, even square root, is going to outpace a log function. And so this limit for the real variable function does not exist. However, when we were doing that theorem about if the real variable function converges, then so does the sequence, we weren't able to turn that one around either. If the real variable function diverges, it didn't necessarily tell us about the sequence. But we understand enough about this expression to really say, you know what, that is going to diverge. That is going to go off to infinity. Probably don't want to put that, but the main thing is that is not equal to 0, right? That is going to diverge. That limit is not going to be 0, and so therefore, again, I have found out that this series from n equals 2 to infinity of the square root of n divided by the natural log of n, skipping some of that notation, diverges by the nth term test. All right, let's look at another example here. This is one of the most famous sequences in series. This is called the harmonic series because it's produced by what's called the harmonic sequence. And the very important thing about a harmonic series is that it actually has a lot to do with music and how the lengths of chords can produce harmony when they follow this pattern. So that's where the name comes from. So let's go in here and let's go look at the limit as n goes to infinity. I'll skip some of the notation here of the sequence. Well, we know enough to say that's definitely 0. That limit is 0. But based on this nth term test, that doesn't tell me anything. If the limit of the sequence is 0, I can't say that this necessarily converges. And in fact, let's go and look at this a little bit and see what happens. I'll use GeoGebra this time to show how to do a sum on there. So let's find the sum. Going to use this one. The expression is 1 divided by n is just as easy to type on a keyboard, so I'll go ahead and go with n. I'm using the variable n in that expression. This one we're starting at 1, and I'll first find the sum of the first 10 terms. All right, 2.92 something. I'll find the sum of the first 100 terms, 5.18. I will find the sum of the first 500 terms, 6.79. Maybe the first 1,000 terms. This is just continuing to go up. I wonder if it'll do 10,000 terms. 9.78. So no matter, this just keeps getting bigger and bigger. It doesn't seem to be slowing down. It doesn't seem to be approaching any particular number. So our suspicion is that this series diverges. So that definitely shows us that just because the sequence has a limit of 0, it doesn't mean that the series is going to converge. So what do we do though in order to prove that? How do we prove that? Well, we come up with another test. And these tests I don't have time to prove to you. They are proven in any standard textbook. We can certainly try to talk about it at some point. But for convenience, we're just going to write them down and work with them. The integral test is a really awesome test. It says basically that if you have a function that matches the sequence, so kind of like we did when we were doing limits of sequences, if we find a function that matches the sequence at all of the natural numbers, and that function happens to be positive, continuous, and decreasing for x greater than or equal to 1, or for x greater than or equal to whatever this beginning index is of our series. If that's true, then both the series and the improper integral going to infinity either both converge or both diverge. That's a really powerful statement because it doesn't, like the nth term test, it doesn't restrict us to only being able to say one thing in one particular case. It either are both going to converge or both are going to diverge. So let's look at how we would use that in this case with the harmonic series. So I'm going to I do want to set up some notation here now then. So I'm going to let f of x equal 1 divided by x, and I'm going to let a sub n equal 1 divided by n. Then let's go see if I have all the conditions set up here. F is positive. If I plug in any positive number here, then definitely F is going to be positive for all positive x's greater than or equal to 1. Is it continuous? Yeah, once we get past x equals 0, it's definitely continuous. We know that about this function. And we also know this graph well enough to know that it is decreasing for x greater than or equal to 1. Also, it turns out that f of n, if I plug in any natural number to this function, it's going to give me the same thing as the sequence formula, a sub n. And furthermore, let's go find the improper integral from 1 to infinity of f of x dx. And I really want to go ahead and use the name here because I've been referring to it up here. So I'm going to start by writing f of x, and then I'll go in and put in my expression. We know that we do that by taking the limit as b goes to infinity of the integral from 1 to b of 1 divided by x dx. That gives me the limit as b goes to infinity of the antiderivative here we know is the natural log of the absolute value of x, and we're going to evaluate that from 1 to b. That is equal to the limit as b goes to infinity of the natural log of b. Because b is a positive amount, I can drop the absolute value, and the natural log of 1 is 0, and that diverges. It goes to infinity. And therefore, the series given by n equals 1 to infinity of a sub n, again I want to connect it because I was using names up here to be able to talk about my notation, and then I'll rewrite what that expression is. A little bit more picky than probably a lot of people would be, but I really like how clear this is. So that also diverges by the integral test.